All right, got my table set up. We'll start with a quick survey. Who of you is in the traditional cloud business? Anything to do with cloud computing, AWS, Google? One guy? Okay. So a couple of people. Who's coming from the blockchain world, decentralization world? Okay, so a majority. Okay. Yeah, it's just good to know who we're talking to. Maybe you know a lot of what I'm going to talk about already. Okay, let me just set this up, and let's start. So today I have the honor of introducing you to the challenges we have in decentralized data. And with decentralized data, I mean storage and databases. We will mainly talk about storage for now, as storage basically is already hard to do, but decentralized databases are a whole lot harder to do, just with regular systems that are centralized. So we'll go through the problems that decentralized storage has, that also applies for decentralized databases, and in the end, we're going to have a brief outlook. This talk is supposed to be an introductory talk to the field, provide some key definitions, and explain the problems we have. So I'm in the nice situation that I get to ask questions, and later in the panels, we get to hear the answers. So what's decentralized storage? First, we'll look at the definition of storage in the traditional computer science sense, right? So storage is about retention of retrievable data. And here, right at this point, we see two very important dimensions about storage. First, we need to keep the data stored, right? It needs to be persisted, and it needs to stay there. But at the same time, we need to be able to retrieve it. And if it's only stored and we cannot retrieve it, that's not storage. So it's about both, and keep that in mind. It's very important for later on. This first part is mainly about storing files. That means just binary large object, just bits that we do not interpret any further, right? It's unstructured data. You could also say we don't put it in database schemes or anything fancy. It's just we have a key, that's the file name, and that key basically points to a set of bytes. That's it. Okay, and the most basic form of storage we know, everybody knows, is local storage. And I think that's a nice case that shows the limitations and issues we also see with more complex systems already. So let's start with that. So it's a trivial case where clients write to a local file system. Of course, this local machine is the single point of failure. So if your house burns or if just your hard disk fails, your data is lost. This is pretty fragile, but in practice, it also works pretty well. We got hard disks to a very reliable level, and we do some backups, and with that, we're good to go for many, many use cases on the end consumer side. Of course, this is a bottleneck. So when you start serving data, you also have limited bandwidth, and you only have this one device where you can upload data and provide data from. So of course, this is a bottleneck with regards to providing data as well. And the client is fully responsible for security here. And this is a burden if you want to open up data to the world, as we see with many breaches in naive web servers that get hosted by end consumers, right? Okay, and then as the kind of second level, we have centralized storage, what we all know, what we all use with cloud storage services such as Dropbox, for example. In that model, we have a client, and that client interacts with the storage provider API. It's just a simple endpoint, and it usually offers CRUD operation. That means create, read, update, delete. And it's pretty much what you have on your local file system as well. So you can just read files, update files, delete files, and store files. And here we have the special case that updating is often implemented as just deleting an old file and writing a new file. This will be important later on. What happens behind this API boundary is not really relevant to the end customer, right? And AWS, for example, may spin up a whole bunch of machines in the backend to make sure they provide you with good service guarantees, but we won't know. All we interact with, like with our local file system, is that API. And there can be many, many instances and complicated data durability mechanisms in the backend. We don't know, we don't care. We have different roles in centralized storage. We have that storage provider, and it has that API, and then we have the client. And clients can interact with the system in two roles. Basically, it can either be uploader or downloader or both. With file storage, if we look at the workloads we observe in the real world, it's usually the case that there is much, much more downloading, retrieval of files for a given file than uploads. And with databases, that's very different. Here you oftentimes have many, many updates on data items and then some reads, but that depends heavily on the application. It's much easier to categorize for file storage. Maybe one example here. So the uploader would be the person editing stuff in the content management system for a website and uploading images, for example, to the server. And the downloaders would be everyone who visits the website and eventually retrieves the files. So one of the most popular ones, I just picked one, I could have also chosen Google Cloud Storage or whatever, is Amazon S3. They offer pretty insane availability guarantees. We're currently 11 nines, they say. It costs about 22 USD for a terabyte for a month. And they offer variants of encryption, so it's basically up to the user to choose whether they want no encryption, client-side encryption, and take care of key management themselves, or whether they want AWS to also take care of their keys and do server-side encryption and protect the keys in their own service. So the capacity for the centralized storage provider scales pretty linearly. They can just add new storage to their data centers, and with that, they can offer more capacity to customers. Networks usually a bigger bottleneck here. And the API, as we said, is very simple. So using S3 is quite straightforward. You just upload files into so-called buckets, and the buckets is essentially just a namespace that a user defines, and that's unique globally. And so it's very easy to use, and in cases of like Dropbox, it's even simpler. You install a client and you interact with the centralized storage service just as you do with your file system locally. AWS is, of course, as a centralized provider, trusted with availability, durability, and security. But at the same time, this is their business model, right? So there's very strong economic incentives for Amazon to behave correctly in the sense that they want to ensure that they actually meet these service level agreements, because if there are data breaches, if data gets lost, this will not only cause them to pay, I don't know, fees according to contract breaches or anything, but will also lose them customers they could have had in the future. Okay, now it's slowly becoming more interesting. We're moving into decentralized storage architectures now. What we now have is we no longer have one provider hosted API that is accessible remotely, but we have many nodes that offer their own little APIs and the client interacts with them. This may be hidden from the end user, of course, by providing a client-side API abstraction, but what happens, you independently interact with many of the nodes, whereas with the centralized services, they usually provide you with one endpoint, and then they do routing on their end to different nodes, okay? And what also changes is just how we think of nodes. Before, we had this very well-defined notion, also with regards to physical location and hardware, of what the client is and what the storage provider is. Now we move to nodes. They can be uploaders, downloaders, just like the clients before. They can also be storage providers, just by offering their local storage to the network. So this is kind of where this clear distinction with regards to node capabilities breaks down, but now we rather distinguish by the role that a certain node has within the protocol. So that means I can be a storage provider, I can be a downloader, I can be both at the same time, but physically we're all the same pretty much in that system, right? We have this. It's not super new. We have seen BitTorrent being quite successful, has been started in 2001, I think. And this is a peer-to-peer file sharing network. How it works, you retrieve a file that represents some content. And these torrent files, they essentially contain two things: some checksums that allow you to check integrity after you retrieved files. And the second thing is it contains a pointer to a node that will give you up-to-date location of file chunks that you need to retrieve to later on build the whole thing, okay? So this is what BitTorrent did, and BitTorrent was very successful. In 2007, was around about 50% of internet traffic was peer-to-peer file sharing, not only BitTorrent, but I don't know if you remember, there was Emule, Kazaa, all these file sharing, peer-to-peer file sharing tools you had. And my theory is that this was not only about peer-to-peer tech, but mainly about content, right? With these platforms, you could get all the things you get on Netflix today, just that we didn't have Netflix back then. We also have newer systems. They have a bit of a different goal, but in the end, IPFS is also one of these decentralized storage systems that it has a content addressable storage abstraction. That means files get addressed by their content, usually using a hash function as an identifier for a file. And that means you get integrity checks for free, essentially. You know a file hasn't been corrupted after you retrieved it because you can simply check the contents. And in IPFS, users are responsible for actually pinning files, and pinning files means I make the file persistent on my node by saying I want this thing to be persistent. And they also cache files, and that's just files that get requested often in the network and they keep in temporary storage, okay? But in that system, it's not like when someone uploads a file, it goes onto your machine or something. You actively have to pin it so that it is stored on your machine. Okay, so let's summarize this in these, I call them non-incentivized decentralized storage networks. We have several of these and they are working fine for some use cases, but there's also a couple of problems we have. So peers can go offline at any time, files can be lost. I think everybody who tried to get downloads from BitTorrent knows that oftentimes there's no chunk service available, and then you'll not be able to retrieve the files, and according to our previous definition of storage, you may even argue without availability, this is not a useful storage service at all. Nodes are free to just refuse serving requests. There is no punishment or whatsoever. So how it usually works in the system is there's kind of this assumption of a symmetric participation model that you upload files and download files kind of equally, or at least that you contribute back to the community by also providing files. And there have been some small incentive mechanisms been put into place here. For example, in Emule, you couldn't download if you didn't provide a folder that you share with the outside world. But the trick, of course, was everybody was moving files out of that folder as soon as the download was complete. So the incentive structure was like very easy to trick in the end. Summing up, we have no availability, durability, or performance guarantees in these non-incentivized decentralized storage systems, pretty much. Now enter the blockchain. So what's new? Why are we here? I think it's because with blockchains, we got this new tool that allows us to build better incentive systems in the end, right? You can now program money, you can now link payments to conditions that happen in some kind of network. And that's how the incentivized decentralized storage idea came into place, when you said, okay, now we have all these different nodes and they behave in a way that we do not necessarily want to. Can we not use the blockchain to build a crypto economic protocol so that they behave in a way that it benefits the overall network? So the idea behind this incentivized decentralized storage systems is to use crypto economic protocols to ensure the desirable properties. And we'll go into these properties a bit more in a minute. Usually, not always. I mean, there's design options, but usually they're backed by blockchains to support these crypto economic protocols in the most proposals. And I observe generally two major directions you could go in when building such a crypto economic incentive system for decentralized storage systems. One is you try to kind of replicate AWS S3, right? You try to build a kind of file storage service based on peer-to-peer contracts. So I enter an agreement with you for you to store a file for me, and then I can retrieve it and I pay you for that. And the idea is that the file is stored as long as I provide payments, and if I stop paying, then you can forget the file again. It's like AWS 3. I can also actively ask for you to delete it. It's also a possibility. The other direction some projects go in is more a permanent file archive. So the idea is that we build a kind of storage layer where no bit is ever lost, right? This is a very huge, global, reliable data lake, you could say. And then you need to build a different incentive structure, of course, an incentive structure that discourages ever losing data. And I think we'll probably see that on the panel. I hope that we have projects that go in both of these directions, and it will be very interesting to see where that discussion leads to. So when you're trying to build these systems, there are tons and tons of challenges. Some are more tightly linked to the crypto economic protocol design than others. Some, like security, you could kind of put on both sides, I would say. So with your crypto economic protocol design, you need to ensure that data is stored durably, that data is available at all time, and that the cost is low. And why is that linked to crypto economics? Well, depending on your fee model and depending on the overhead that is caused by your blockchain backend, the costs very much depend on that protocol as well. And then you have all these other properties that are maybe a bit less tightly linked to incentive systems, arguably. Security, scalability, like in security, how do you protect clients from traditional attacks like distributed denial of service? Yeah, scalability, as I said, performance, like how can we get latency down and throughput down, all these kind of things. Let's briefly look at that, what that means and how they, which role they play in these systems. So durability basically asks the question, will my data still be there in the future? So if data is stored durably, it will never be lost. So you can also define it as the probability that data will survive permanently. So in such a system, we want to be sure that even if storage providers or nodes fail, the data can never be lost. Traditional approaches in computer science to that are replication, that simply means storing multiple copies of that data, or some advanced forms like erasure coding, which lives somewhere between replication and sharding. And in that, you take your data, you blow it up with some additional information and split it into fragments, and then you have a set of fragments where you do only need k out of n of these fragments to rebuild the original file. So that means you can tolerate a certain number of nodes that store these fragments going offline without suffering from data corruption. So the question we will ask to the panelists is, what's your approach to ensure durability? Which measures do you have? Which of them are traditional? Which are crypto economic? Like that, that's what we can discuss. Availability now answers the second part of the question that we already kind of implicitly saw in our definition of storage. Is my data accessible at the moment, right? So it's a probability that a request is served successfully by the system when called. And yeah, we can ask multiple questions in that direction also to the panelists. So how can a client be sure that the file is actually stored without retrieving it? With Amazon S3, we just look at the file explorer, and since we trust them anyways, we kind of assume it's there. In decentralized storage systems, this may be harder to figure out. How do we agree on SLAs? Which SLAs can we even provide in a decentralized setting? And what's the overhead of data retrieval? There are different schemes that are proposed for data retrieval, which is tightly linked to availability. That means when I, as a client, want to retrieve the data that someone stores for me in the system, how do I do that? Do I have to do prepayments? Do we have a micropayment scheme where I potentially pay a little bit of an upfront fee, then I get a chunk, I pay a bit more, get another chunk, and I do that until I get the file? What do I do if I do that process? I pay, and then the server does not return the very last chunk, but I already paid the majority of the fees. Like all these questions that come into mind when retrieving data in such a system with an incentive layer. There are different attacks degrading durability and availability, and this is by no means exhaustive. It's just a couple of interesting or well-known attacks. So one is Sybil attacks, and the attack here would be, I just create many identities in that storage network, and then I claim or I sell my service of storing a certain file. And I do that from every identity. So you want to store a file, and you want to store 3 replicas, so you want to store it 3 times. I create 3 identities and store it 3 times, right? What can happen then is that because I'm one person or one entity in the background, I only store the file once, but point to it 3 times, right? So is that bad? Is that good? Of course it's a problem, because if my one physical copy gets corrupted, then my data is gone, right? So from the storage system's perspective, if there's no good incentive mechanisms in place to prevent that, or protection versus that attack, then it could look like your data is highly replicated, but in the end there's a single point of failure, right? So we need to prevent that. There's outsourcing attacks, and here the idea is, I know you store tons of data, and I can reliably retrieve that data from you with very low latency, right? What I do then is, I also offer to store replica of that data that I know you store anyways, and whenever I get a request, I simply retrieve it from you and pass it on. So I get fees for storing data, but all I do is actually forwarding to you in case you request the data. So this boils down to ensuring that you have physically independent copies of data, that your replica are actually physically distinct and stored on multiple nodes, right? There's also other attacks like generation attacks where you do not store the data itself, but instead a small program that can generate the data when run, and that can be much more succinct in representation in storage. But that's not really I mean, that's mainly a problem when you use the metric of overall file or data volume stored within your incentive protocol, because then it allows people to store less than they claim to be storing. It's not an obvious attack like the first 2, and it can only work in systems where you use that metric as part of the incentive protocols. Then there are some more challenges tightly linked to incentive systems, and this is basically about how do you do good crypto economic protocol design, because this is a very recent discipline. You could argue game theory has been going, studying design of such systems for a long, long time, but now we have this link established between traditional computer science and game theory, and it's not simple to do proofs that protocols work as we used to do or still do in traditional computer science protocols usually. So this became a lot harder, and this is kind of addresses the last point here. How can you even ensure when you're using a crypto economic protocol that it works correctly? You can do potentially game theoretic proofs, but that's very hard. What you can also do is you just put up bounties. You kind of say, there's a lot of money on the line now, right? People store tons of files in my system and accrue over time, and there hasn't been a breach, and there's so much money at stake now. If the system was insecure, an attacker would exploit it and get all the money. So it's kind of an implicit proof, not really a proof, right? But it's battle tested, and that's what you can also do as a kind of reinsurance that a protocol works, just to battle test it on a small scale and then grow and grow and grow. Then you have different trade-offs that come with your choice of the blockchain system and the backend, right? Do you go for a custom ledger that you spin up and that is purpose-built to serve your purposes, or would you rather, to not have lock-in effects, have a general purpose blockchain like Ethereum backing your storage system? There is also design challenges that where you try to link this physical world of storage with your incentive system, because then you need to disincentivize or punish people for doing things that are bad for the system. But in many cases, this is very hard to detect or cannot be detected at all. And one example of this is, for example, a client requests data and the storage provider actually serves the data. And then the client says, I didn't receive that data. And what do you do in that case, right? I mean, I told you what happened here, so in that case it would be simple. But if we observe this behavior from the outside, there's no way we can tell whether the guy actually provided, or at least we have to think about very hard how we could tell that the guy actually provided the data to the relevant node and that node actually received it. There was no network outage. So establishing accountability in these incentive systems is quite a hard problem and cannot be done for all properties. Cost is, of course, important. You have some overhead when you use a blockchain as your backend, of course, because you need to do transactions, pay transaction fees, and these blockchains may be congested, all that kind of stuff. But what's important, it's not as simple as plugging in more hard disks to serve users' needs, where cost scales very predictably, but you may have coordination overhead due to a more complex cryptoeconomic protocol or transaction fees that kind of drive your cost up. At the same time, you could argue that the centralized storage market may not be super competitive because there's relatively few large providers that offer these enterprise-grade services that people or companies really want. So it could be that they charge you with too much, right? Sure, you can go to that little independent small hoster that only takes $10 for a terabyte for a month, but most enterprises don't feel comfortable with it because you trust AWS because it's kind of also battle tested and very large and all that kind of stuff, gives you strong SLAs. So maybe there's a niche. Also, the marginal cost of plugging in your hard drive or providing the hard drive you have in your computer at home is close to zero, right? You have that thing, you bought it already, and if you now open it up to the outside world, there's very little cost to you. It may consume a bit more energy and eat up some of your bandwidth of your personal internet connection or whatever, but generally it's cheap unless you start buying new hard drives. But just by using old hard drives and providing to the outside world what we already have in unused storage capacity today can become quite it's quite a big capacity that we could potentially leverage. What's interesting to ask the panelists whether they have more insights on how the prices compare today and how it's going to be in 5 years. Can we go below the $25 or $22 S3 charges? Can we go much lower with a bit weaker SLAs, or is it completely unrealistic to be there in the next 3 to 5 years? Okay. The large providers, they have security experts because there's just so much at stake, right? They try to protect their infrastructure. They protect the network entry points a lot. They have security specialists. But in decentralized systems, we also need to protect the nodes, because when I know that a certain file is stored at 3 physical nodes that I can directly address in the peer-to-peer network, it may be straightforward to just DDoS these nodes and make a file unavailable. So how do we protect the nodes that participate in our storage systems from such attacks? How do we make sure there's no data loss due to these attacks or data theft by using a weak client-side security setup in the home router or something, right? Key management. Many people in AWS just store data in clear text because they trust that AWS does not use their data in any way they would not want to, or they trust that they don't look at the data at all. But in that decentralized storage network, I don't think people will go with that model, right? They will not assume that people will not be able to see what you store on their machines on behalf of you. So I would argue that encryption is probably going to be a default for several reasons. It may be legal issues. What if someone tries to store clear text data that is illegal on my node? And or what is if I want to store my, I don't know, bank statements somewhere in that network and everybody can see them? It's not that simple in practice, because you usually chunk data and distribute that data, and then it has to be rebuilt, and it depends on how you allocate files in the network. There's also different choices. But overall, encryption seems to be a good idea. But now, the people uploading the data or interacting with the storage network, they are responsible for key management. And we know very well from Bitcoin and other cryptocurrencies that people are very bad at key management. So many Bitcoin are locked up. How many files would be locked up in that system? What's good here, though, is after your file is locked up and the time period that you paid for with regards to storage runs out, then the clients that store it for you or the storage providers that store for you, they can simply forget the data, and it's kind of more self-healing than forgetting private keys in cryptocurrencies. Okay, scalability. AWS just plugs in new hardware, right? And it scales pretty well if they manage to not overload the network. So what's the bottlenecks with decentralized file storage? Are there any? Is it that the blockchain used to build incentive protocol is going to get overloaded really quickly as we scale to petabytes of data and many users? Or is it going to be able to cope with that through clever mechanisms? So what do the projects think? What are the limits to scalability and overall capacity today, in the future? Are these considerable challenges, or is it straightforward to do? We'll hear in the panel, I hope. Performance. Usually data centers are built with super low latency and high throughput connections to internet backbones, right? So they can reliably provide files to the outside world, and it mainly depends on the client's connection to the backbone, how high or how low latency is. Now, with decentralized file storage, we may introduce another unknown, and that's the connection from that endpoint that stores files to the internet backbone that's like well connected with all the other major backbones. So do we expect to have a big impact on latency when we deliver files in decentralized systems? Can we maybe compensate for that by retrieving many chunks in parallel, recombining them at the client side, and getting much higher throughput that way? Of course, latency and throughput are two things, right? But still, there may also be advantages and not only disadvantages when we move to a more decentralized model and distribute the files over many locations globally and split them up. Also, what's a common practice with cloud offerings is that you co-locate your application code with the data you store in one data center, because then you get that super low latency connection, right? Few people would use Google Cloud Storage and use Amazon EC2 compute services, because usually you go with one provider, then you're in one data center and you have super low latency connections. So is there an equivalent we can think of in the world of decentralized file storage? Is this an issue? Is this a non-issue? Let's discuss. User experience. For me, this is a big one. Usually when you call these decentralized storage services, you just use an API key, you go there, invoke the interface, and you get your data, right? There's not that much you need to do, but you retrieve that API key once and you're good to go. Maybe you install a client-side SDK, but that's about it. And now the question is, in these decentralized storage systems, incentivized decentralized storage systems, where we use blockchains or other incentive engines in the background, which additional steps do I need to do as an end user to participate in the system? Do I need to synchronize a blockchain first? I think everybody experienced it on their phones. That is super annoying to sync, even with the light client protocol, to the Bitcoin network before you can do mobile payments because you're in the coffee shop and you would like to pay, but you haven't been online for 3 days, and then, it's inconvenient. Do you need to acquire specific tokens, or can you use crypto tokens that you already own anyway? Are there bridges so that you can easily exchange tokens in a fast and decentralized way against more established tokens that you may hold? Do I need to install a wallet just to store files, or is there a better way? And also with regards to usage patterns, what's a very common use case for file storage is I put a file somewhere on AWS and then I link to it from a web page. And all the person needs to do, they don't even need an API token. I make them available publicly, right? They can just visit the site and query the service, and I pay for their retrieval. Can we have the same model with decentralized file storage, where I can just embed files and then retrieve them, and another person pays for that? I think we've seen things like that in the wild, in the Ethereum space, but it's just also an interesting question. What does usage look like? What's the lock-in effect? What's the cost of entry? There are many other questions. I don't think we have time to go through all of them, maybe just quickly. So another question is, how tightly should the blockchain and the storage system be coupled? Does it make sense to use a specific blockchain that within its consensus protocol, for example, uses storage-specific metrics, like in Filecoin, for example, where they do proof of space-time-based mining, where the idea is you provide capacity to network over a long time, and you get a voting right or the right to propose a new block in proportion to the volume and the space-time, volume times time that you provide services to the network for? Or should it rather be like in Swarm, where you use the Ethereum blockchain as the backend, which has non-specific, non-storage-specific consensus mechanisms? Is there a legal risk when participating? I mentioned this. What if someone stores illegal files on my node? We've heard cases from companies not adopting Bitcoin because there may be some shady data stored somewhere in history. It's like, is it references to shady data, or is it shady data?
There's weird stuff in there.
Okay, yeah, so these kind of things, right? We want to prevent that. There is also proposed mechanisms like plausible deniability. Maybe you can go into more detail on that. I think it's a very cool idea to prevent these kind of things. Also, there's compliance with GDPR. I think that's more a matter of how you set up contracts with which nodes. Can you make sure that data remains within a physical location or region? Can we do updates? How can we protect user privacy in P2P networks? I think we've seen from TU Berlin here actually interesting analysis of the Zcash peer-to-peer network, where they managed to figure out a lot about Zcash payments by network analysis that kind of broke the anonymity guarantees that were established on the protocol level by Zcash, just because it was so clear what data is sent to which node by whom, and the peer-to-peer network was very easy to observe, and you could learn a lot and too much from it. So how do we protect from that kind of stuff in these networks? Okay, that was a lot of questions we will hopefully get back to during the panel. Now just quickly a 3 to 5 minute outlook on why decentralized databases are even harder. So in decentralized databases, the same problems apply. It doesn't get any easier, because what databases are in comparison to file storage is you have structured data now, right? You know more about the data that you store. You can put them in schemas, you can store them in different ways depending on the schema. You want to be able to do querying on that data, and you want to be able to update chunks of that data. In file storage, it's usually okay because we do not interpret the data when we want to update a file to just throw it away and store a new one. Because we have very different workloads in database systems where we update only small pieces of larger records oftentimes, that's what we do not want to do. We do not want to throw away the whole file, but we want to replace only a small sequence in that whole stream of bytes that we store on the nodes. So we have structured mutable data now, and that poses a new set of challenges. It changes things completely, and it adds more complexity on top of what we already have as challenges here, right? And then another key issue from my perspective is what we have in decentralized file storage is we have data at rest. And we know very good techniques to ensure integrity of data that we put somewhere, right? We do hashes, and then after retrieval, we just check that the data hashes to the value we expect. We can publish that hash through side channels, whatever. So there's tons of integrity checks. But with databases, we usually do not retrieve the full records. We only ask for small chunks of that overall data. And that means what the database needs to do is some processing. It takes the data, applies some functionality, does some processing to filter out the relevant bits, maybe aggregates several of these bits it filtered out. So querying with, I don't know, in SQL you have sums, you have averages, all that kind of processing that's going on before you respond to the client. So the problem shifts completely from only providing integrity guarantees in the case of decentralized storage to having to ensure that this processing within the database, the decentralized database, happens correctly, right? We move from simple integrity checks to making sure that computations happen correctly, which is also like a whole new set of challenges. We have query support, and even in traditional database systems, this is an issue when you move to distributed systems. I mean, AWS hides it all behind an API, but internally there's so much engineering and high-tech stuff going on just to make sure that you can efficiently query very large data set that gets updated a lot, and is split or sharded across different nodes and not all on one machine. Because what you try to avoid is having to do expensive distributed joins. That means that you essentially retrieve data from many, many nodes and recombine it and process it on another node before being able to return a request. What you would rather want to do, you store your data in a way that is specific to the queries you expect to happen. We call the schema denormalization. So we store data in a non-SQL-like fancy fashion just so we can respond to queries that we expect very quickly. But I mean, this is already hard in traditional databases, or I mean, it can be done, but it's not straightforward to do, and that's things we need to think of when we do decentralized databases as well, of course. So the design space is huge, and you probably have heard of the cat theorem. This is kind of what a design space boils down to with traditional distributed systems. Now add incentives on top of that, and that's what you get for decentralized database systems. So in my opinion, it's hard, but it's also space where a lot of research can happen, and it's a super interesting field. Because now you get one more tool, crypto-economic protocol design, that you can use to solve issues that traditional computer science has not been able to solve within this framework, right? I would like to conclude this talk by showing you some statistics and asking you one question. Back in the days, in 2007, we were quite on track with decentralized file storage, right? 50% of the internet traffic, I found this in an IPOC study, was peer-to-peer file sharing. So that includes uploads and downloads. In 2018, BitTorrent was only 3% of downstream traffic. I mean, this comparison is not perfect because I didn't manage to pull up the very relevant data to directly compare, but we know the amount, the share of overall traffic of peer-to-peer networks went down by a lot. I think it's mainly due to content, right? We used to get content from these platforms that we couldn't get anywhere else. And then it shifted to FTP, HTTP-based content provisioning, and then this got professional, and then we got Netflix, right? But there may be other reasons for this. So, yeah, also that, sure. Yeah, so the capabilities of the clients that like used to be more more equal in the network. That's a good point. It's like spread a lot, so we want clients to be very light. But I think just like we have light clients and blockchains, they're not perfect. We could have the same kind of idea. That doesn't mean we could not do it. We also could have a decentralized network service these light client devices. So the question that I want to ask, and maybe the panel also has an opinion on that, is decentralization itself a value for an end user? Or do these statistics tell us that there needs to be an additional benefit for users to ever adopt this? That means we need to work to be cheaper, more secure, have superior content, be more censorship resistant, because I think that's also actually a use case that drives adoption, and we can observe it today with Bitcoin payments, right? Strict capital control, more Bitcoin traffic and usage. So the question is, where are we going? Can we achieve that? And is decentralization a value in itself? Okay, so thank you for listening. With that, I'll conclude the talk.